We're now going to consider one of the most important methods for trying to evaluate integrals, and it's the method of substitution. So we know that if we have an integral of this form, I can see that that's a chain rule. And so if I rewrite that as an integral of a derivative, then I can work this out very easily. But sometimes we can't see that, but that it is a chain rule. So for example, this one, it might be fairly clear to you that this is the integral. So I've got an outside function and an inside function. Well, the inside function is this 1 plus x squared, and its derivative is supposed to be on the outside here, and it is. Derivative of 1 plus x squared is 2x. So this is of the form, it looks like I've got a derivative of something. So the f prime is this square root somehow. So it's not exactly clear what my composition is, but I can see there's some sort of composition here. Well, it turns out that what I've got is something like this. Now, I'm missing some things because we can see that if I take the derivative of this, there's going to be an extra 3 halves that'd be out in front that's not here. And so, the point I'm making is this is not always easy to reproduce the composition that you're taking the derivative of. I can sort of piece it together if I work through it. So we want a method to help us undo this chain rule that was done and then be able to find that integral. Now we won't turn it into this, but we have a method called substitution that will give us a different way of evaluating integrals that come from someone having applied a chain rule. So we do use the fact that I'm looking for an inside function and its derivative on the outside. So when I see an inside function, I'm going to substitute in for that, hoping that this was a chain rule and that I'm going to be able to undo that chain rule. And so this integral, I'm going to make a new integral. Usually in mathematics, when we use a substitution, it's because we're trying to make something look simpler. As I was showing you here, it's a little bit too complicated for me to figure out exactly what derivative I have here. So I'm going to make things simpler by getting rid of some of the complicated stuff. I'm going to get rid of the 1 plus x squared. So that integral right now is going to have a square root of u in it where that 1 plus x squared was. And then I got to get rid of everything. Everything that has x's in it has to be converted to u if I'm going to do a substitution. And so this is where we finally use this dx. I can create a dx from this statement by taking the differential of both sides. And so I get du, taking the differential, is the derivative of this, which is 2x dx. And so this says that I can replace the 2x dx by du. So everything else that's in this integrand gets replaced by du. So the u replaced the 1 plus x squared, the du replaces 2x dx, and here's my new integral. Now again, I don't see it necessarily as something like that, but this is an integral in u, and I don't care what u is right now, it's a variable. And I can apply a formula because this is u to the 1/2. I can apply one of my antiderivative formulas, the power rule. This becomes u to the 1/2 plus 1 divided by 1/2 plus 1 plus a constant. That is, this is u to the 3/2 divided by 3/2 plus a constant. Or, if you like, 2/3 u to the 3/2 plus a constant. Now, that's not answering the question that was asked. I was asked to integrate this, and I've got an answer here in u, so I do need to convert my answer to an answer with x's in it. But you go back to your substitution, and now you undo your substitution, meaning now I put the 1 plus x squared back in. So I get 2/3 1 plus x squared to the 3/2 plus a constant. And so I'm claiming that's the antiderivative in this case. And the nice thing about antiderivatives is you can take the derivative to see if it really worked. Now I'm running out of room here, so I'm going to do it up here. I'm going to take the derivative of what I came up with. 2/3 1 plus x squared to the 3/2 plus a constant. When I take the derivative, I've got the 2/3 there. I'm going to bring the 3/2 out in front. And then the 1 plus x squared is the inside function. So this 3/2 is going to get reduced by 1, so then I put the inside function back in, and then I multiply by its derivative. Sorry, I ran out of room. And then derivative of that constant 0. But we can see this 3/2 and 2/3 is going to cancel, and there's my 2x square root of 1 plus x squared. So it does work. That is the antiderivative. We know that by checking, unless we somehow made a mistake going forwards and backwards, this is the correct antiderivative. So that's our process. It's called a U substitution. And we can see, in general, what we're looking for. We're looking for an integrand that has a function raised to a power. That's an inside function. And we're looking for an integrand where it has a trig function with some function inside of it. So I've just kind of generalized statement there. Now, a U substitution will work if we substitute for f as long as an f prime is somewhere in my integrand as well. It doesn't have to be exactly f prime, as we'll see, but something that's at least the variable part has to match up with my derivative of f. So that's our goal. Look for an inside function raised to the n, or an inside function inside of a trig function, make a U substitution. So here's an example. When I'm looking at this integrand, I see an inside function. I'm going to substitute for that, hoping that this will be some sort of chain rule that was applied, and I'm undoing that chain rule. Now, you always look first to see if it's in your list. Obviously, this is not in my list of integrals that I know how to do. So then your next option is to do some algebra. Well, there's no algebra to do when you got this all mixed together like this. And so then a substitution is typically the next thing in line. So I do substitute in for that inside function, and notice I can tell already this is going to work. I do the differential, and you can see it's not 3x squared, but there is an x squared there. So I can convert this by recognizing that u is replacing x cubed, so I'm going to have a cosine u, and then what's left is x squared dx. Well, from here I can see that x squared dx is going to be 1/3 du. So I can manipulate my substitution after I've done it, or my differential, either one. But I can see that I'm going to have 1/3 du replacing the x squared dx. And now I've got something that's in my list. I've got 1/3 integral of cosine. And that's in the list, as I said. That's going to be sine plus a constant. And as before, I want to get the substitution. I want to put the x back in. So I undo my substitution by saying this is 1/3 sine of x cubed. You can check it very quickly that this works. You take the derivative of sine and you get cosine. Put the inside function back in. So now I've got cosine x cubed, and then the derivative of the inside function is 3x squared. Cancel the 3. So you can formally check it, or just kind of spot check in your mind to make sure it looks like it's going to work. So there's an example of both types. One where you have some function on the inside. It was the square root, so to the 1/2, and then we have a trig function. Well, let's try this one. So now I see a trig function. This is not in my list. You could try to do some sort of trig identities or whatever, but I don't think it's going to get any nicer than this. If I could somehow get the sine to cancel, that'd be different, but this cosine is not going to cancel a sine. So I'm kind of stuck with trying a substitution and recognizing that what I have here is cosine x squared. That's what that notation means. So if I rewrite it that way, it's very clear that this is an inside function. And I'm going to try to substitute in for that, hoping that's part of the inside function from a chain rule. And it will be if, when I take the differential, I end up with some form of the derivative in the rest of the integrand. And notice, when I take the cosine, I get minus sine dx, and there it is. It's not exactly what I have, but I don't need exactly the same thing. I missed the constant part. The constant multiplier can be wrong. It's the rest of it, the variable part, has to be there. And so if I substitute that in, I now have u squared, and this says that sine x dx is going to get replaced by minus du. Just bring the minus to the other side. And I'll just go put the minus. I know it's a constant. I'm just going to go ahead and pull it out right when I put it in. So that integral converts to just minus the integral of u squared, which is definitely in our list. That's just a power rule. It becomes u cubed over 3. And once I'm done evaluating the integral, put my variable back in. So this is going to be minus cosine cubed x over 3 plus a constant. It's very easy to check. Take the derivative of this, you get the 3 out in front, cosine squared, because you reduce the exponent by 1. Then you have to take the derivative of cosine, which gives you a minus sign. Well, the minuses will cancel, the 3's will cancel, everything will get you back to there. So again, doesn't hurt to spot check in your mind or formally go ahead and take the derivative to be sure you're getting that integrand back. So that's the method of substitution. We'll work some more. We'll also look at how to deal with definite integrals when we do a substitution.